Right, so in this one we're going to talk about geometric programming, denoted as GP. We're first going to discuss what monomials and polynomials are and some of their properties, that is, closed under addition, multiplication, what happens when I multiply a monomial with a polynomial, and so on. Next off, we're going to see a GP in its genetic form or polynomial form. Then we're going to move on to see how to convert a GP, which is in general not a convex optimization problem, to a convex optimization 1. That is, we're going to see two forms of a GP problem, in polynomial form, which is not convex, and in convex form, which is clearly convex. And last but not least, we're going to see two important examples. First one is going to introduce the problem of Frobenius norm minimization with diagonal scaling. That is, given a certain matrix with a certain structure, how can I minimize its entries via the Frobenius norm? And in example 2, we're going to see a nice application of volume maximization of a certain room or certain box, given some sort of limitations on surface areas and aspect ratios. So without further ado, let's get started. Right, so geometric programming, hereby denoted by GP, is a family of optimization problems that are not convex as is. That is, in their natural form, they're not convex. But these problems could be transformed to convex optimization problems by using some simple change of variables. Now, before I go ahead and define what a GP is, we have to define some sort of mathematical functions that are called monomials and posynomials. Monomials are functions that take in a vector and return a scalar such that the domain of f is in Rn++. And the function takes the following form. So if x is my vector and x is composed of components such as x1, x2 down to xn, then a monomial would look like this. So it's the first component raised to something real, so let's say alpha 1, multiplied by the second component x2 raised to alpha 2, and so on, multiplied by the last component raised to power alpha n, where all my alpha i's are real, so no complex exponentiation, and we can have a constant here, c, which has to be positive. Your alphas could be negative, meaning that your x's could appear as fractions in the denominator. So an example could be something like this, so 2x1 root x2 over x3 to the power pi, for example. So here my alpha 1 is 1, my alpha 2 is half, and my alpha 3 is minus pi. Oh, and c is 2, right? Now, in algebraic terms, a monomial indicates that exponents should be non-negative integers, but this is not the case here. So our exponents, alpha 1 down to alpha n, are free to wander in R. So they don't have to be integers, and they definitely shouldn't have to be positive. They could wander anywhere in R. Okay? Now, a polynomial is just a sum of monomials. So likewise, your f going from Rn to R, where your dom ff is R plus n, fx is a polynomial when it is a sum of monomials. So in that case, fi is a monomial, so it has the following form right here. And here we have k sum of monomials, so I've got f1 plus f2 down to fk possibly. And in this case, we refer to a polynomial with k terms. So similar to polynomials are a sum of exponents of x, right? This polynomial is of order n, given that an is non-zero. So likewise here we've got k some monomials, and to close this description of a polynomial, we restrict all the c's to be non-zero. Okay, so there's no need to say, oh, this c is zero, this c is zero, set them all to zero, and then back to zero. No, they shouldn't be zero. But we're sure we have a sum of k monomials. Now, some nice properties about polynomials is that they're closed under addition. So if I grab a polynomial, let's say f, which is a sum of monomials, so the generic form of polynomials is just to set an index k on each and every one of those exponents and the c. That being said, I could write it as follows. So ck, x1 to the power alpha 1k, x2 to the power alpha 2k, right down to xn to the power alpha nk. So if I grab another polynomial, g of x, which is also order k, let's indicate now different parameters. So dk, x1 to the power beta 1k, to xn to the power beta nk. So let's force my ck's to be positive, as a monomial would do, right? And all my alpha nk's are in R. Likewise, the dk is positive, and the beta nk's are all in R. So if I add f with g, I will get a polynomial. That being said, polynomials are closed under addition. The proof of that is fairly straightforward. And by the way, we could have two polynomials of different order. So this could have here a p, right? So they need not to be only of same order. It applies to two polynomials of different orders. So with that being said, you just add them, right? You will get another polynomial. Let's say here I've got an hk, x1 to the power, I don't know, let's call it gamma 1k down to xn gamma nk. And since we could write it in this form, then sum of two polynomials is again a polynomial. And here we're going to have k plus p terms, where let's say ordering doesn't matter. So my hk is going to have ck, it's going to take values ck if k is between 1 and k. We're going to take values dk if k is between k plus 1 to k plus b, right? So I'm just choosing those terms, and then I choose those terms. And a similar definition holds for the gammas. Not only are polynomials closed under addition, but they're also closed under multiplication and non-negative scaling. That is, if I grab two polynomials and multiply them with each other, so fx times gx is again a polynomial. Also, multiplying a polynomial with a constant or a scalar, which is non-negative, is again a polynomial. Now, monomials, go back here, that's not true, because if I add two monomials, I'm not a monomial anymore. I'm a polynomial. So you can't say the same thing about a monomial. However, monomials are closed under multiplication and division. That's really easy to see. All you have to do is just put two monomials, let's do the division. So this could be written as c over d times x1 to the power alpha 1 minus beta 1 down to xn alpha n minus beta n. There you go. You have a form of a monomial. Your c is a c over d. Your alpha 1 now is an alpha 1 minus beta 1. And there you go. It has the same form as a monomial, and thus it's a monomial. And to be more concrete, c over d is still positive, since c is positive and d is positive. And your exponents are still real, because the difference of two real numbers is again real. This is the division. It's also closed under multiplication. Now, if you grab a polynomial and you multiply it with a monomial, you get a polynomial. Likewise, if you grab a polynomial and divide it by a monomial, again, your result is a polynomial. That's also really easy to see. Why is that? Because if this is my polynomial, let's say, and I divide it by a monomial, all my exponents are going to be subtracted by the corresponding exponents in the denominator. Therefore, all I did was just subtracted my exponents in all the k terms, and I divided all the ck's by the corresponding scalar in the denominator. That's fairly simple to see. Okay, now we describe the math that we need to define a GP, which include monomials, polynomials, and their properties. That is, polynomials are closed under addition, multiplication, and scaling. However, monomials are only closed under multiplication and division, and not addition. Now, without further ado, let's get started with what a GP is. A GP is an optimization problem of the following form. So minimizing a certain objective function over x, a vector x, subject to the following constraints. So some inequality constraints and other equality constraints. Now, why did we talk about polynomials and monomials? Clearly because we're going to use them here in the problem. So my f's should be polynomials, my hi's have to be monomials. If this is the case, then guess what? You've got a GP problem. Now, to be more concrete about this, the domain of the problem, of course, because polynomials, the domains of polynomials are in Rn++, as we saw here and here. So D of this problem, the domain, has to be Rn++. Now the problem as is not convex. Why? Polynomials are not convex. You might encounter problems that are not in this form, but could be transformed to a GP. For example, if you encounter such a problem with an additional constraint saying, I have one f p of x, a polynomial, is less than a monomial, h k of x, for example. Okay? If you encounter such a constraint, it's not found here in the generic form of a GP. It's not there. But this constraint in particular could be transformed to this guy right here. How? Well, we just said that a polynomial divided by a monomial is again a polynomial. And hence this is the equivalent of saying f, let's say, p plus 1, we create a function fp plus 1 of f is less than 1. And what is fp plus 1? It is nothing other than fp divided by hk, right? Why? We just divide hk on both sides, and we are sure that fp plus 1 is a polynomial. Likewise, if you see two polynomials equal to each other, that is, hk of x is equal to hk plus 1 of x. It's not in the generic form of a GP, but could be transformed to a constraint that looks like this. How? You just divide by hk plus 1 on both sides. You get an hk plus 2 of x, which is hk over hk plus 1, is equal to 1. And this guy is now one of the generic constraints of a GP problem. Why? Because the division of two monomials is again a monomial. So here, as you can see, we're exploiting the properties of polynomials and monomials. We're seeing different variations of a GP problem by just, flipping around with the constraints. So I'm going to give you a small example. Let's say I'm maximizing x over y subject to between x is between 2 and 3. This is just out of Boyd's book. Straightforward example. X squared plus 3y over z less than root y, and x over y is equal to z squared. Now, first of all we have to do is identify the cos, which is clearly this, and this, no problem. This is a monomial and hence a polynomial. So this is written as x and y to the power minus 1, and hence has the form of C1, x1 power alpha 1, x2 power alpha 2, where C1 is 1, alpha 1 is 1, and alpha 2 is minus 1. So no problem with this. Now let's go ahead and look at the constraints. The constraints could be easily converted to ones that correspond to a generic GP problem. How is that? Let's first, I don't like how this looks like. We've got two inequalities. This is lower bounded and upper bounded. None of this in the generic GP problem. So how do we go over this problem? So before I go ahead, I'm just going to cover this by f0 of x, where f0 of x is x, y minus 1, and a tick next to it. That is, we see that we have a polynomial called monomial, but monomial is a polynomial, but not the other way around. So we're maximizing a polynomial subject to 2 is less than x, but x is less than 3, so I splitted this inequality to two inequalities, and nothing goes down here, and x over y is equal to z squared. Now, we just said if we encounter a polynomial less than a monomial, it's easy, right? And even more, this is really straightforward. So all I have to do here is multiply by or divide by x on both sides. So I'll get a 2x minus 1 less than 1. This is done. Why? Because this is a polynomial, right? And right here it's done. So just divide by 3. You will get a 1 over 3 x less than 1. Done, right? So I'll just rewrite this as maximize f0 of x. I'll just put a reminder here what f0 is, what f1 is, and what f2 is. Good. We're left with an inequality constraint, so the guy on the right-hand side should be a polynomial less than 1. So how do I get a 1 here? All I have to do is divide by root y, and we shall get x squared y to the power minus half plus 3y y to the power minus half, and we forgot a z in the denominator. I'll just put it as z minus 1 is less than 1. Now, we've got two y's here, so this could be rewritten as 3y half z minus 1, and there you go. The guy on the right-hand side is a polynomial, this is a monomial, and this is another monomial. So my f3 of x is x squared y minus half plus 3y half z minus 1, right? Okay, 2 fi of x less than 1. This time I is 1, 2, and 3. Where is 3? It is this guy, okay? Which is here. We're left with one equality constraint, and make sure your equality constraint should only be a monomial equal to 1. So let's divide by z squared. We'll get x. We have a y in the denominator, so y minus 1, and z squared, z minus 2 is equal to 1. And there you go. So your h1 of x should be this guy. Y minus 1 z squared subject to fi of x less than 1. I goes from 1 to 3, h1 of x is 1. This is a G. So the point of all this was an example showing you that sometimes you encounter GP problems that are not clearly in the GP genetic form. You need to do some manipulations to have, the correct form. So as stated previously, geometric programs are not convex optimization problems, but they could be transformed to convex ones by suitable change of variables. And we'll see that right now. So before I go ahead and convert a GP or rewrite a GP in convex form, it's worth noting some few of the many applications of GP. So here's a very nice tutorial on geometric programming by Stefan Boyd, Shangjen Kim, Lieven Vandenberghe, and Arash Hasibi. They've done a really good job in, explaining very clearly how GP modeling is done, what a GP is, its applications, and many more. So the interested reader is referred to this tutorial. Another very nice paper I found was by Meng Chan, who works at Princeton. Well, in this paper, or overview, I would say, it describes many applications of geometric programming to communication systems, that is, information theory, coding and signal processing, network resource allocation, network congestion control, and queuing theory. It also describes the usefulness of geometric programming to communication systems, and to be more precise, to stochastic models and deterministic models. So here's another specific paper on geometric programming with many interesting references. Some direct applications of geometric programming are those involved in power control. So we know that in a model where, if you're familiar with wireless communication systems, when you have a wireless network with n pairs, and here your problem is to allocate powers to certain links. You've got a power budget. So the problem here is to find the best strategy to transmit powers in good links, to do it in a smart way. This problem could be formulated as a geometric program. A lot of nice stuff has been done in this paper. Go check it out. An old paper, but it's really worth reading. You'll enjoy it, trust me, is this paper right here. It's by a guy that used to work, or who had his thesis probably funded by the Army Research Office. His name is Richard James Duffin. He's an American physicist known for his contributions to electrical transmission theory and to the development of geometric programming. So in this paper, he describes how a geometric program could be linearized, that is, write it as a linear program. It also describes some conditions and why, in precise, a duality gap, which we will be explaining in future lectures, cannot occur in geometric programming. So he's showing some sort of equivalence between a geometric program and a linear program. Another interesting paper might be the following paper. So binary power control for the SRM, sum rate maximization over multiple interfering links. This is related to the power control problem we saw earlier, but in this case right here, you've got multiple interfering links. Okay, that's it for some applications. Now let's see how to convert a GP, or how to rewrite a GP in convex form. So again, let's say I am minimizing a polynomial subject to inequality constraints on polynomials and equality constraint on monomials. This is a GP. So the first change of variable is to have your yi, is to introduce variables yi that are equal to log of xi's. So a logarithmic change of variable, or equivalenty xi is e to the power yi. Now each one of those polynomial functions, fi of x, is a sum of ci x1 alpha I1 multiplied down to x alpha I n, where I goes from 1 to k. If we plug this change of variable, we will have ey1 alpha I1 down to eyn alpha I n, right? That is to say, you can write this as ci ey1 alpha I1 down to ein times yn. Now let's express the ci as e power bi, if you will. So we get e bi, which serves as a slope and the exponent, then e alpha I1 y1 down to e alpha I n yn. Since the base is common, we could write this as exponential bi plus alpha I1, y1, down to alpha in, yn. If I denote the vector alpha I as alpha I1 down to alpha in, then this could be written as exponential bi plus alpha I transpose times vector y, where vector y contains y1 down to yn, right? And therefore my problem could be stated as, to minimize, so all my fi's have this form, so I'll just replace, I'll get a sum I from 1 till, now to distinguish the orders, because they need not all the fi's have the same order, I'm just going to say a k0 order for the cost. So here, exponential bi and bi0 plus alpha I0 transpose y. And the reason I'm putting a 0 is that I don't want those to be the same as the constraints, because they need not be the same values, subject to some I1 from ki, since each constraint has a different order. Exponential bi, say j, is alpha I j transpose y less than 1. And the equality constraints are monomials, so exponential, let's call those CIs, let's call the slopes, or let's call the slopes here di plus, let's call this something else, bi transpose y equal to 1, where I goes from 1 to p. The problem as is still not convex. The costs and the constraints are not convex. We're left with only one simple transformation, which is to take the logs of all the functions we have. That is, minimizing, a function is the equivalent of minimizing its log, because log is an increasing function. So no approximations, no, it's the same. You're minimizing the same thing. And hence, we could take the minimum of the log of the sum of exponentials, subject to log on both sides, and the inequality constraints less than log 1, which is 0, where we've got n such constraints. And the log of the exponential is just the exponent, right? So we're left with a di plus beta I transpose y is equal to 1. I goes from 1 to p. Now, the cost. The inequality constraints are convex functions, and the equality constraint is an affine function. And hence, this problem is now convex. Now, this problem is usually referred to as a geometric program in convex form. Maximizing or solving this problem will result in values of y, which could be easily changed to the x domain, which is what you need, by this simple change of variable. xi is the exponential of yi. So to go back to x domain, all you need to do is to compute the logarithms of your y's, right? You might be wondering, how is this not convex, and how is this problem, which is equivalent, convex? Well, it's not written in convex form, but under this nonlinear change of variable, it becomes convex. Now, to do the distinction, we're going to refer to this problem, which is not convex, as a GP in polynomial form, right? We've got all those polynomials around and everything. We'll just refer to it as that. And the one in convex form will be referred to as a GP in convex form. Okay, all my polynomials are monomials. In that case, the log will cancel your exponential, and you're left with affine functions. That is to say, a GP in that case would be nothing other than a linear program. That said, we can consider a GP to be, let's say, an extension of an LP. Okay, so far we've talked about monomials and polynomials, what a GP problem in polynomial form, or how a GP problem in polynomial form looks like, and its corresponding convex form. Now let's go on to applications or examples of where GP shows up. Let's say I've got a Frobenius norm diagonal scaling problem, which is I've got a matrix M, which is square, dimensions n, and this matrix is associated with a linear function that maps a vector onto another. So let's say I've got a vector x, Rn, and a linear mapping would be to multiply m by x to produce y, right? Now, let's say we're in a situation where I want to scale my coordinates. That is, I have a diagonal matrix D, which is composed of elements D1 down till Dn, and zeros here, since it's diagonal. And a change of bases or a change of variable in x would suggest x bar is d times x, and similarly y bar is d times y. So to write y bar as a function of x bar, all I have to do is to replace it in the equation y is equal to mx. Let's express x in terms of x bar and y in terms of y bar. Now, given that d is non-singular, that is, none of the diagonal components are 0, I could write the following. So x is d inverse times x bar, likewise y is d inverse times y bar. Placing those two here, I will get d inverse times y bar is m d inverse times x bar. Now multiply by d on both sides, I will get y bar is d m d inverse x bar, right? Now the problem is this. Suppose we want to choose the factors d in a way that this quantity, or this, is as small as possible. Now how small? We need to define a certain measure. Which measure? We're going to choose the Frobenius norm. That is, I want to minimize as much as possible the entries of the matrix D and D inverse. So minimize with respect to D1 down to Dn. Since m is given, I'm not going to minimize with respect to those components, but with respect to D. So the problem is how to choose D such that this matrix is as minimum as possible in the Frobenius sense. Now, using the Frobenius definition is if I have a matrix A and Frobenius norm square, and A doesn't need to be a square matrix, so it's just the sum of squares of the components in A. So Aij squared. Applying this here, we get the equivalent problem of dm, d inverse, ijth entry, all squared, right? Now, how does this matrix look like? If we denote m's entries by mij, then you can easily verify that dn d minus 1, its ijth component looks like this. So mij di over dj. So the squaring should look like this, the I squared over dj squared. Now this problem is an unconstrained geometric problem, of course in polynomial form. That being said, if you want to solve it in a convex optimization form, you have to do the transformation we discussed. So why is this a polynomial? It's easily seen. If you look at those as, if you look at mij squared as the constants, so they're the ci's or cij's in this case, and you've got a di square with a dj minus the power minus 2. So the exponents are either 2, minus 2, or 0. When is it 0? It's when I is j. So those guys cancel out. So that's it for example 1. So another really interesting example is when you have a certain room. Let's imagine this is my room, right? This is the height, this is the width, and this is the depth. Now, what you're targeting here is what you desire is to maximize the volume of your room given some certain constraints on the dimensions, h, w, and d. What are those constraints? Well, I'm forced to respect some certain aspect ratios. That is, h over w is bounded between alpha 1 and alpha 2. Likewise, d over w is bounded between beta 1 and beta 2. And let's not forget, I'm trying to maximize the volume. That is, h, w, d. H times w times d. Not only this, I have some other limits to respect. That is, I've got a area of a floor. So let's say this is my floor, right? Let's call it AF, that I shouldn't exceed. That is, the area, the floor area, which is simply length times width, or W times D, should be less than a certain area AF. So this is less than AF. Likewise, the walls, the total surface area of the walls should not be more than a certain value. So I've got 4 walls, out of which 2 have areas HW, and the other 2 have areas HD. So the total surface area should be bounded by AW, which is a wall. So this problem happens to be a geometric program. The first thing you should pay attention to here is that you have a maximize. And you're not allowed here to insert a certain minus. It doesn't make sense. So your domain here is Rn++. So what people do here is that since, and even if you insert a certain minus, it's not going to work because, okay, you're going to get a min here, but remember, your cost should be a polynomial, and a polynomial has a positive constant, C, right? So a trick here is to minimize the reciprocal. That being said, you could minimize 1 over HWD. That is the equivalent of minimizing H minus 1, W minus 1, and D minus 1. Your C here is 1, positive, so no problem, right? Now likewise here we've got 4 inequality constraints right here, which could be written as alpha 1 less than H over W, H over W less than alpha 2, also beta 1 less than D over W, and D over W less than beta 2. Got a WD less than AF, and a 2HW plus 2HD less than AW, right? So let's do the same tricks we did before. Let's try to find the 1 here, divide by H over W. So those constraints are the equivalent of, if we divide by H over W over here, we get alpha 1, W, H minus 1 less than 1. Polynomial, no problem. Same thing goes here. Alpha 2 minus 1, H, W minus 1 less than 1. Polynomial, no problem. Right here, same thing. Divide by D over W, beta 1, W, D minus 1 less than 1. Polynomial, no problem. Next, same thing here. Beta 2 minus 1, D, W minus 1 less than 1. Polynomial, no problem. See what we've got here. Divide by AF, get AF minus 1, WD less than 1, polynomial, no problem. And last but not least, divide by AW over here, you will get, so this W is a subscript. It's not a W here, okay? This is a subscript. So divide by AW, you will get 2 over AW, HW plus 2 over AW, HD less than 1, polynomial, no problem. So this is a GP and polynomial form. So this is it for this lecture. We've done quite a lot. We've defined what monomials and polynomials are, seen how a GP problem in polynomial form looks like, and its corresponding convex form, which is useful when you want to, express the problem as a convex optimization problem. And we've seen 2 examples which show the usefulness of a GP. The first one was to minimize the entries of a certain matrix with respect to diagonal parameters in a Frobenius norm sense. And example 2, where we're interested in maximizing a certain volume of a room or a volume of a box given some certain limitations and aspect ratio constraints. This is it for this lecture. If you found it useful, please subscribe to my channel and leave a comment if you have some sort of questions. I'll be glad to help, and I'll see you in future lectures.